In this lesson, we're going to look at the mole-to-mole ratios between substances based on a balanced chemical equation. This is called the mole method, and we're going to use the stoichiometric coefficients, so the numbers before each substance in a chemical equation, as the number of moles of each substance. Instead of thinking about molecules, we're going to think about moles. So 4 moles of aluminum reacts with 3 moles of O2 to produce 2 moles of aluminum oxide. Let's look at an example of how we get these ratios from our balanced chemical equation. We can get relationships between any pair of substances in a reaction. It doesn't matter which side of the reaction they're on. For example, for every 1 mole of propane, we need 5 moles of oxygen. Because the coefficient for propane is 1 because there's no number there, and the coefficient for O2 is 5. For every 1 mole of propane, we can generate X moles of carbon dioxide. We see the coefficient of 1 before propane, and we see 3 for CO2, so we're producing 3 moles of CO2. To produce 4 moles of water, we need X moles of oxygen. In our equation, we see that we have 4 as a coefficient for water, and we're talking about oxygen where we have a 5. We need 5 moles of oxygen. These ratios can be written for any pair of substances. This could be 2 reactants, 2 products, or 1 of each. We've already learned several things or several types of relationships that help us convert between different units. For example, grams to moles, we use molar mass, which has units of grams per mole. Between the mole and actual number of a thing, we use Avogadro's number because Avogadro's number, 6.022 times 10 to the 23rd, things per mole. Remember, it's just a counting number, like 12 in a dozen. A mole is 6.022 times 10 to the 23rd in a mole. Between mass and volume, we use density. For gram to kilogram, or for any different metric prefix, we're going to use the meaning of that prefix. Remember, put the 1 with the prefix, put the meaning with the base. Between molecules and atoms, we use the subscripts from the chemical formula. And what we've just learned, moles of A to moles of B. Notice that A is any substance in the reaction and B is some other substance in the reaction. And we're going to use the coefficients from our balanced chemical equation. The problems we do today will focus just on that mole-to-mole conversion. But what we'll see is as we add on to this and progress through using stoichiometry, what we're going to see is we'll use lots of different conversions in one problem. Note that this has to be from a balanced equation. So every equation you have, you need to first check that it is balanced before you start doing any setup or calculations. Over the next several lessons, we're going to explore more parts of this diagram. But what we're going to focus on right now is the fact that we have a known and an unknown. And note that they do not have to be a product and a reactant. They can be 2 products, 2 reactants, or a product and a reactant. It just matters that we have one thing we know something about and something we're trying to find out. And we're going to specifically focus here on the middle of this diagram. Moles of A, whatever that may be, using the coefficients from our balanced chemical equation to get 2 moles of B. And we're actually going to set these problems up much like our dimensional analysis problems that we did earlier in the semester. We have a balanced chemical equation, and we're asking how many moles of CO2 are formed when 0.5 moles of C3H8 is burned. Just like with dimensional analysis, we want to figure out what we're starting with, what we're trying to find or the end, and what relationships we might know that are going to help us get from the start to the end. Let's read through the problem again and find out where we're starting and ending. How many moles of CO2 are formed? That gives us our end. We're trying to find moles of CO2 when 0.5 moles of C3H8 is burned. And that's our starting point. We know that we're going to go from propane to CO2, and we can write a relationship between those. 1 mole of C3H8 to 3 moles of CO2. That's our mole-to-mole ratio between those two substances. Just like with our earlier dimensional analysis problems, We're going to start with our given value, the 0.5 moles of C3H8. We know that moles of C3H8 must go on the bottom because we want to cancel those units out. And the relationship we know with moles of C3H8 is to 3 moles of CO2. A couple of things to note here. This relationship is based on the balanced chemical equation. This relationship depends on only those coefficients in the equation. It doesn't matter how much of the substance we actually have. It's always going to be based on that balanced chemical equation. The second thing you want to note is we always need to write down our substances. Note that we're going from one substance to another. It can be easy to mix those up and invert the relationship. So always make sure that you have the right coefficient or the right number of moles with the right substance. Now we can cancel out moles of C3H8, and the units we're left with at this point are moles of CO2. We do the calculation and we get 1.5 moles of CO2. Well, some may be able to do this problem in their head because we know it's a 1-to-3 ratio. We only have a half a mole. They will get more complicated. So it's important to know how to set up the problems so that you can do this for any combination of numbers. How many moles of water are produced when 10 moles of C3H8 is burned? We're given a balanced chemical equation. We're going to do the same thing as before. Our start, our end, and our relationship. How many moles of water is going to be our end because that's what we're trying to find. Our start is the 10 moles of propane because that's what we're given. And the relationship we know between those is 1 mole of C3H8 to 4 moles of water. We're going to start with the 10 moles of C3H8. In the denominator, I know that I have to have moles of C3H8, and I know that I have 1 mole of C3H8 to 4 moles of water. That's the mole to mole ratio that comes from our balanced chemical equation. Now I can cancel moles of C3H8, and when I do the math, I get 40 moles of H2O. Note that the coefficients from a balanced chemical equation are considered exact numbers, so they do not play a role in determining the correct number of sig figs. How many moles of CO2 are produced when 6 moles of oxygen is consumed? We have our start, our end, and our relationship. We want to end with moles of CO2. We start with 6 moles of O2. And the relationship between them is 5 moles of O2 to 3 moles of CO2, because those are the coefficients from our balanced chemical equation. That is our mole to mole ratio between those two substances. We start with 6 moles of O2. We know that moles of O2 needs to be in the denominator, and our 3 moles of CO2 is going to go on top. So 3 moles of CO2 to 5 moles of O2. Cancel out moles of oxygen, and I'm left with 3.6 moles of CO2.